dynamic CMOS logic, what happens is that there are two phases of operations. It happens with the clock signal. Whenever the clock is equal to 0, we call it as an pre-charge state. If a clock equal to 1, we call it as an evaluate state. Means until the next phase is occurred, or until the next stage has been has arrived, this particular logic is going to be stored in that particular what is that, capacitor, or it is stored as a capacitance. Next, once the next stage is arrived, then that logic will be sent to the next phase of the design. So that is the meaning of it is a temporary storage in the temporary storage of the output levels that will remain only for the short period of time. The static logic retains its output levels as long as the power is applied. In the static, it is not the same. In the static, what happens, until the power is supplied, the output will be remain there. But in the dynamic, what happens, depending upon the switching of the clock, which is connected as an input to the transistors, the output will be stored there for until the next clock arrives. So that is the meaning of it's a temporary storage logic. So now here in the dynamic logic is normally done with the charging and selectively discharging the capacitances. That is wherever the capacitor circuit nodes. Now here, if you want any of the operation to be any one part of that model to be operated very fastly, there you'll try to discharge that particular capacitor, so that the discharging means that output has been obtained. Then so that it gives a path for the next stage of the design to obtain its output. So how the output is obtained? Only when the capacitor is fully charged. So if a capacitor is fully charged, we say that output is obtained. And if the capacitor is fully discharged, we say it is giving a path for the next phase of the design to obtain its output. So that's the meaning of selectively discharging the capacitor wherever you require the speed of the particular signal, or wherever you need the performance of the signal to be enhanced. So let us see now. It is a pre-charge phase and the evaluate phase. In the pre-charge clock, it is the clock to charge the capacitance. That is a clock signal equal to 0 is a pre-charge state. Evaluate state is a clock which is used to discharge the capacitance depending upon the conditions of the logical inputs. So now we'll study about this one in the coming slides. What is pre-charge and what is discharge and what is evaluate with respect to some examples. So let us see now advantages of this dynamic CMOS logic over the static. It avoids the duplicating of the logic twice as both N tree and the P tree as in the standard CMOS logic. So here you'll not be having any kind of duplicating of the what is that N trees or the P trees. P trees or N trees are nothing else but N networks, NMOS network and the PMOS networks. You'll not be having a duplication, because in the static we have seen that it requires some N number of gates. If there are N inputs are there, then it requires 2 N types of devices. But that kind of duplication is not taken place here. Typically, it can be used in very high performance applications. The dynamic CMOS logic is used in the very high performance application. Next one, it is used in the sequential memory circuits, and also it is used in amenable to the synchronous logics. It is used mostly in the synchronous logics and also in the sequential memory circuits. Next one, it's a very high density achievable. High density achievable means you can fit large number of devices in the networks, in the trees. In the NMOS or PMOS trees, you can fit more number of transistors. So it's a denser logic, and it also consumes a lesser power in some cases. Now coming to the disadvantage, we'll talk about some cases in the next slides. Coming to disadvantages compared to the static logic, the problem with the clock synchronization and timing. So now here what happens is that since we are having 2 different clocks, the clocks has to arrive at the same time. If the clocks are arriving at the same time, then only we can say that the inputs which have been given to the particular tree or particular network will be arriving or will be moving at the same time phase. But if one clock is arriving at one particular time and other clock is arriving with a delay, then what happens? The first signal will be going faster, but whereas the second signal, it will be delayed. So that's a major problem. We'll see even that one in the graphs of the dynamic CMOS logic. Another one, the designs is more complex, more difficult. Why? Because more number of trees in the more number of transistors have been connected, and it's also a dense network. So now this is a small explanation about how the CMOS dynamic CMOS looks like. It's like it's a 2-step operation. the pre-charge state will be there and evaluate state will be there. Why do we use a pre-charge state? The pre-charge state is mainly used in order to charge the signal, and that is to the high, to the logic high, and the evaluate state is mainly used to discharge this clock signal. CS means it's a clock signal. This is the 5 which you see. This is a clock signal. Here also you can see the clock signal. So now whenever the clock is equal to 0, if a clock equal to 0, the PMOS is turned on. Whenever the PMOS is turned on, what happens? The output is fully charged. Why? Because the VDD will flow to the clock and it will be stored. It is stored as a charge in this capacitor. That's why the capacitance will be formed here. But whenever it is clock is evaluate means what? Clock equal to 1. If clock equal to 1, what happens? The PMOS is off and NMOS will be turned on. If NMOS is turned on, then the complete whatever the charge is stored, that will be discharged depending upon this transistor's inputs. Let me say now, if this transistor is turned on, then this complete whatever the capacitance is stored in the previous state of pre-charge, it will be discharged from this capacitor to the ground terminal. So that's the meaning of how the evaluate and pre-charge will be working. You can see now, this is a pre-charge state. In the pre-charge state, what happens? The capacitance is, you can see the high value. So if it is equal to 0, the value will be high. Whenever this is 1, that's the evaluate state. Again, it's a pre-charge state. So this one is regarding the clock, this inputs, and these are the two pre-charge and evaluate state functions. And this is a small explanation about what is meant by dynamic in order to give an idea about this one. Now let us study in detail about what is dynamic CMOS logic. In the dynamic CMOS logic, the circuit relies on a complementary storage of the signal values on the capacitance of high impedance node. This one here is it will rely on the temporary storage logic. Why? Because the signal is stored here temporarily for the phase of this clock. If the clock is equal to 0, then the capacitor will be stored, or it will be filled with the capacitance, or it will be filled with the capacitor, or the capacitor is fully charged. Whenever the clock equal to 1, this PMOS is turned off and NMOS is turned on. That's why the discharging takes place. So it's a temporary storage logic here, and it requires n+2 devices. This particular dynamic CMOS logic requires n+2. What is this meant by n+2? Since here this block is a pull-down network. If there are n number of pull-down network, then the n transistors will be n+1. It will be n+1 plus 1, the PMOS. So it will be like n+2 devices required. Whereas if I consider for the CMOS structure or static CMOS structure, for the same operation, what is this operation? It is like both NMOS are in series. Both NMOS are in series. If NMOS are in series, means it's an B.C plus A. It means it is like the operation for this one is Y equal to, for this network, the operation is Y equal to A plus B dot C. Y equal to, this is operation, this is a Boolean equation for this network. It is A plus BC, that is B dot C. So now if you can see what will be the value of this one. A plus B dot C means what? You require, there are 3 different inputs here. 3 different inputs means you need 3 PMOS and 3 NMOS. Though ultimately what will be there? 3 PMOS, 3 NMOS. It's like now we need 6 different transistors here. 6 different transistors. But here you can see there are only 5 transistors. So number of transistors have been decreased for this one, for this particular device, or for this particular operation. And this is a block diagram of dynamic CMOS logic. First, you'll be having a PMOS to the clock will be connected, and here down it is a footer for this NMOS is connected. And now in between there will be a pull down network. This is a pull down network which defines your Boolean equation, and this MP and ME are compulsory. This is a pre-charge MOSFET and this is a evaluates MOSFET. MP means pre-charge MOSFET, ME means evaluate MOSFET. Clock. This is a clock signal which you supply here. and this one denotes your Boolean equation. And this is the same one which we have taken. It is a now here inputs are changed here, so I can write it as A dot B plus C. The Boolean equation here it is. Since both the NMOS are in series, the operation will be A dot B for NMOS, and it is these two are in parallel to the C, so it will be plus A dot B plus C. Y equal to A dot B plus C is a Boolean equation, and this is a circuit diagram for Boolean equation Y equal to A dot B plus C using the dynamic CMOS logic structure. So now let us study in detail about this one. Can anyone tell me what is a Boolean equation of this circuit? What is the Boolean equation of this circuit? All three NMOS are in series, and again those three NMOS are parallel to the two NMOS which are again in series. If that is the case, your Boolean equation will become as A1 dot A2 dot A3 plus B1 dot B2. So that becomes your Boolean equation for this one. Why? Because all the NMOS will be in series only for dot operation. So now since this dot operation, A1 dot A2 dot A3 dot, this will be taken in bracket plus this both are again in a series, so it is B1 dot B2, and this B1 B2 is in parallel to the A1 A2 A3, so I taken the plus in between, so it is A1 A2 A3 plus B1 B2. So that is your Boolean equation, and that further Boolean equation, this is your dynamic CMOS logic structure. So let us see the operation of this circuit. In the dynamic CMOS logic structure, here a single clock phase is being used, phi, and that happens upon the evaluate and pre-charge state. Evaluate means what? Clock equal to 1. Pre-charge means what? Clock equal to 0. So now I have taken clock equal to 5. Whenever the clock equal to 0, that is a low state. Now what happens? Only the PMOS is turned on. PMOS is turned on, and footer NMOS is turned off. Now in this case, what happens? The VDD will be dragged to the output, so that the capacitor here, whichever the capacitor is connected to the output, will be fully charged. So that's why you can see here now the PMOS pre-charges the transistor MP, charges output to VDD. So now this Vout will become equal to VDD, approximately it will become VDD. So therefore it will remain in the linear region during the final pre-charge state. So because whenever it is 0, whenever the clock equal to 0, your output is going to be 1. The output is going to be 1. Now, during this time, the logic input A1 to B2 are active. Are active means what? Here, all the transistors are working depending upon the values which are given to here, given to this gates A1, A2, A3, B1, B2. So now, whenever this one, and you can even see in this one, since the clock equal to 0, this one MA will become off. Therefore, no charge will be lost from the Vout. No charge is lost from the Vout means, since these are active, if all the NMOS are on, then only the VDD will discharge, then only the Vout will discharge to this particular point. But since they are not on, only few are on, few are off, they are active in some other case, the output will not be lost. So whenever the clock equal to high, what happens? If clock equal to high, because of that one, the PMOS is turned off, NMOS is turned on. NMOS is turned on. If NMOS is turned on, what happens? Allowing for output to be selectively discharged. Selectively discharged means what? The output, if B1 and B2 are turned on, since we both are NMOS, whenever I supply logic 1 to this both the inputs, if these are turned on, then only the output can move from this path to the ground. That is the meaning of selectively discharging. Or else if these three are turned on, then the output can move from the capacitor through this A1, A2 and A3. So this is the meaning of what is meant by selectively discharging. Can you tell what is the first point? First point is like whenever the clock is equal to 0. If clock equal to 0, the gate voltage which is supplied here is 0. And this is one of the query which has been asked to me right now. So now if clock equal to 0, the PMOS is turned on. The PMOS will be turned on whenever the gate voltage is equal to 0. NMOS will be turned off whenever the gate voltage is equal to 0. It means that at gate voltage equal to 0, the PMOS will be turned on and NMOS will be turned off. So now in the clock 1, whenever the clock equal to 0, the PMOS is turned on, a channel has been created. Through that particular channel, the VDD will be now moves from VDD to the output. Why? Because a potential difference has been created. But due to that potential difference, in order to have an equilibrium in the potential, the VDD moves from the logic 1 will move from this point to the capacitor, which is stored, which is connected to the output. In that case, the capacitor will be fully charged. That's the meaning of this one. The output MP charges the output to VDD. Means the logic 1 will be obtained at the capacitor which is connected to the output. So next one, whenever the phi is equal to high, the MP is turned off and NMOS evaluate will be turned on. If this is turned on, depending upon this transistor, depending upon the on stage of this transistor, the output will be discharged through the ground. That is the meaning of selective discharging. The selective discharging will be taken place, allowing for the output to be selectively discharged to the ground depending upon the logical inputs. Logical inputs means this A1, A2, A3 gate inputs. If A1 to B2 inputs are such that conductive path existing between Vout and ME, then the Vout is discharged to 0. If all these transistors are turned on, if all this transistor A1, A2, A3, B1, B2, B3, B2, all are turned on means what? I have given a logic 1 to all the gates of this transistor. If it is turned on, then whatever the complete, there is a complete path has been created between the Vout and ground. So the complete discharging of the signal takes place from the output to ground. That's the meaning of this one. The output will be discharged to 0. Otherwise, the Vout remains to VDD. If this is not turned on, let me assume that this A2, A3 and B2 are turned on, but A1 and B1 are not turned on. Then what happens? There is no other way for the output to discharge to ground. So the output will be VDD only. Why? Because there is no channel created for this A1 and B1. The output cannot discharge to the ground. So that's the meaning of, otherwise the Vout will remain at VDD. This is another network. Another network, you can see the operation here. Pre-charge state and evaluate state. Pre-charge means logic clock equal to 0. Evaluate means clock equal to 1. Okay. Now here we'll complete this particular part, and we'll wind up, or else I think it's time up as of now. Why? Because I have come up with more.
Time is up.
Yeah, time is up because I have come up with nearly 60 slides today in order to deal these topics, 60 to 65. But it's a very huge concept. I hope you have understood now, up to now.
Yes, sir.
The dynamic CMOS logic means, always keep in your mind, it will be having one PMOS as a pull-up network and as a pull-up device, and a NMOS as a pull-down device, which is taken as a footer. In between, you'll be having your Boolean equation network. See, this is a Boolean equation network. This is a pre-charge transistor, and this is a what is that? Evaluate transistor. But in between, all these are the Boolean equation. What is a Boolean equation? A dot B plus C plus B dot E whole bar. So like that, you should try to understand the network. In tomorrow's class, we'll try to complete as much as we can, and we'll see that operations. Okay, thank you everyone. Thank you for listening to this particular class.
Excuse me, sir.
Yeah, please tell me.
Sir, something there is a doubt with 412. I'm unmuting.
Could you please tell again? I'm unable to hear you.
Something there is a doubt with 412, it seems.
Something there is doubt?
There is a doubt for
Me, sir.
Yeah, tell me, ma. Who is that?
Before slide, once open, sir. Before slide.
Yeah, is this one?
Yes, sir.
Yeah, please tell me, ma.
Sir, here, when clock is high, NMOS will be off, na, sir.
When clock is high, NMOS will be turned on.
PMOS will be
PMOS will be off. Yeah.
Then how will VDD output, sir? It is open.
Yeah, just a minute. See here. Whenever the clock is 0, what has happened? Let me assume that first stage is my clock equal to 0. Then what happens? this will be turned off. This NMOS is turned off, and this will be turned on. In this state only, the VDD will be pre-charged. Means what? Your capacitance is now fully charged with a value of VDD. Okay? Is it okay, Mano? That is the previous state. Now let us come to your point. Your point is what? Whenever clock equal to high, whatever you told is correct. The PMOS is turned off and NMOS is turned on. Is it okay? Now you're talking about this one, right? V out remains VDD. Could you please talk to me? Could you please talk to me, anyone?
Yes, sir.
This is your point. How it is V out will remain VDD.
Yes, sir.
Yeah, how the V out is remain VDD means what has happened in the previous state, your capacitor is fully charged, right? Forget about now in this state, the PMOS is off. Whenever the capacitor is fully charged, see this point. If A1 to B2 means all this transistor, 5 transistor, which is an A1, A2, A3 plus B1, B2 operation, are such that conducting the path exists. If all are on means what? For all this value, the gate voltage is given as zeros. For all this gates, the input is given as logic 1. Whenever the gate is given, gate input is given as logic 1, all the transistors will be turned on. Then VDD V out will become 0. Why? Because the previous state VDD will be moving to the ground. But otherwise means what? If these transistors are not turned on, that's why I have given example. If A2, A3 and B2 are turned on, but A1 and B1 are turned off. Turned off means there is no path from this point, from this drain of this A1 and from the drain of B1 to reach to the drain of A2 and drain of B2. There is no path, so you cannot expect the VDD, which is stored as output, to go to the ground. Because of that reason, it cannot go to the ground. I hope you can understand Telugu, right? Because of that reason, the VDD cannot discharge to the ground because these both are off. Otherwise, the V out remains VDD. I hope your point is clear now.
Sir, if all are off means also
If
output
all are
will
off
be
means your
0.
output is VDD.
Okay.
If all are off means there is no point for the VDD to the capacitor to discharge to the ground. Why does the discharging takes place? Because of the potential difference. Potential difference vallane
Yes,
the
sir.
discharging will take place.
And when all are on, the capacitor will discharge.
Yeah, when all are on, the capacitor will discharge.
Okay.
Or else, if these two are on also, if all these are off and these two are off also, there is a path created from this point to the ground. Even in that case also, the capacitance will discharge. Capacitor will discharge.
Okay.
Okay?
Okay.
Okay,
Yeah,
sir.
okay. Thank you, Ma. Thank you. And tomorrow's class, we'll study in more detail about few more operations and we'll go to the domain logic.
Sure.
Okay, thank you. I'm leaving this session.